Welcome, everyone. We're just going to give it a few more minutes because I know some people may still be lingering in the snack break. Almost evening. Okay, just 1 minute and then we'll get started. Okay, it's 4 past, so this is probably all we're going to get. Let's go ahead and get started. Welcome, everyone, to the last session on a late Friday afternoon at IETF 121. This is the MLCODEC, Machine Learning for Audio Coding Working Group. It doesn't bode well for slide control. So note well, there are several BCPs that you should familiarize yourself with if you're going to be participating in IETF meetings and list activity. You should be familiar with the standards process, the working group processes, the anti-harassment policies, code of conduct, copyrights, and especially the patent and what your participation entails in that. Namely, there are obligations to file IPR declarations against any IPR that you are aware of, and your contribution requires that. We also have an anti-harassment policy that you should familiarize yourself with. If you run into any issues, please contact a member of the Ombudsman team, and that's available at itf.org/ombudsteam. For in-room participants, please make sure you're using the MLCODEC client. You can use the on-site or the full client. The on-site tool just doesn't have the audio and video support, but you can still raise your hands to get in the queue. And you can also participate in polls. For the remote participants, please use the full client so you can get audio and video, but please keep your audio and video off unless you're chairing, presenting, or speaking when told. Links to the agenda and any issues if you have with MeetEcho, please report them. We need a note taker for this session. The notes are already pre-populated with the agenda, and we just need the high-level comments about any directions or actions that the group takes, not a verbatim log of everything that's said. Thank you, Jonathan. Okay, so our agenda today, we have the Opus extension mechanism from Tim, the deep redundancy draft updates from Jean-Marc, speech coding enhancements from Jan, new work that's being proposed for a scalable quality extension by Jean-Marc, and also some simplifications by Jean-Marc. Any bashing or changes? Okay. Tim, you are up.
All right. So do you have the slides to share, or do I need to go find
You want me to share them, or you want to share them?
If you could, that would be great.
Sure. Able to see that now?
Yep. All right, so there's been no change to the actual draft since Prague. We had a couple of outstanding proposals, but the one I'm going to talk about in this session is the repeat these extension proposal. So next slide. So to refresh people's memory, the use case for this was to reduce the overhead of using the same extensions for multiple Opus frames in the same packet, motivated mostly by using either hybrid mode or CELT in 60 millisecond packets, which people do to reduce the IP, UDP, RTP header overheads. So the benefits of doing this is that we can reduce overheads even with just one extension that appears in more than one frame. The savings scale with the number of frames and their number of repeated extensions. They apply to any extension, so you don't need to use up extra IDs or signal things, special things in SDP. It integrates well with non-repeated extensions like Dread. And if we don't do it now, it would be a breaking change to extension parsing to try to do this later. The costs, of course, are there's additional implementation complexity. Mostly on the decoder side, it's entirely optional for the encoder. And the extensions in a frame are no longer guaranteed to be physically contiguous in the packet, which, might surprise people, but I don't think is really that serious a cost. Next frame or next slide. So there have been a couple of updates to this since Vancouver. First, using repeat these extensions with the L flag set to 0 with a long extension followed by short extensions can now elide the final length, even if those short extensions have a payload. And the second is that using repeat these extensions with L equals 0 and no long extensions increments the current frame number. That one I think we had discussed on the list, but is new since the last meeting. And finally, there's an implementation at gitlab.sif.org, so you can see what the actual code complexity of doing all of this stuff is. Next slide. So to go over those two changes in a little bit more detail, this was actually a change suggested to me by Jean-Marc, and I'd sort of, said, oh, that's too hard to do, too much work to do back when we had 3 different implementations of iterating over extensions in libopus, but since it's now been consolidated to one, the patch for this was actually pretty simple, and I had some time on a plane, so I went ahead and implemented it. So previously, the length of the final long extension is, if it's final long extension being repeated, is admitted even if it's followed by 0 or more short extensions if they had no payload. So those extensions didn't need any space, so the payload for the final long extension was still just the rest of the packet. Now you can omit the length of that final long extension even if there are short extensions with a payload that are repeated after it. So you have to track how much space is needed by those short extensions. There's a new failure point in the parsing, so if you don't have enough room to fit all those short extensions and the implied length of your long extension would be negative, that's a problem. But on the other hand, some other condition checks are slightly simpler, mostly those dealing with the next change. So next slide. Just to give an example, so here we have 15 bytes of padding, and we start off with 2 extensions of the first frame, 1 long extension of length 4, and 1 short extension with a 1 byte payload. And that's followed by the repeat these extension with L set to 0. So that will now consume the rest of the packet. In this case, this packet only has 2 frames. So after that, we have another long extension, and this one does not need to code the length. And then following that payload is the payload for the short extension. So basically, when you get to the long extension, you can see you have 6 bytes left in the packet. You save one of them for the short extension that needs to follow it, and that implies that the length of the long extension is 5 bytes. If you were to remove the final 6 bytes of this packet, then parsing would fail, because when you went to decode the long extension, you wouldn't have enough room for any length, not even 0. I see Jonathan Lennox at the queue.
Yeah, Jonathan Lennox, clarifying question. Does this mean that repeat these extensions implies that the long extensions have to be the same length?
No. So you notice in this case, the first long extension is length 4, and the last long extension is length 5. So
okay,
it's
great.
Yeah, it's figuring out the length based on the amount of space left in the padding.
Oh, okay. So it's basically because the short extensions are fixed length, so you just subtract. Okay, cool.
Yep, exactly. All right, any other questions on that change? Great, so next slide. So if you have long extensions, normally the L equals 0 flag on a long extension means it takes up the rest of the packet. And with the previous change, that makes repeat these extensions with L equals 0 work the same way if it has any long extension being repeated. But if there are only short extensions being repeated, then you can't do that, right? Because you don't have a payload that can take the rest of the packet. So what do we do? I had a couple people make this suggestion to me in comments before I presented in Vancouver, and so I can take a hint, and I went ahead and made this change. And basically, if you have only short extensions being repeated and you set the L flag equals to 0, normally you would continue decoding non-repeated extensions back in the frame where the RTE byte was coded. But if it use L equals 0, it now advances to the next frame. So it can save the 1 byte cost of a frame separator in some cases. Next slide. And here's an example of that. So we start off with a short extension with a 1 byte payload. We do repeat these extensions with L equals 0. And so now we have a 1 byte payload for a short extension in frame 1. And then extension decoding continues in frame 1 now instead of frame 0. So now that there's a long extension whose length also gets omitted because it's the last extension in the packet. But you notice we didn't have to code a frame separator to advance to frame 1. All right, any questions about that example? Okay, next slide. So popping back up to the question of whether or not we should actually do this proposal, the main benefits here are bitrate savings. So it may be helpful to take a little bit closer look at what exactly those savings are. There's a formula there at the top. It's basically the number of repeated extensions plus 1 times the number of frames minus 1. The plus 1 is because you also save frame separators, and the minus 1 is because there's no savings in the first frame. You may also save up to 1 length. So if you previously did not have a long extension at the end of the packet, and this now allows you to omit the length of a long extension, then you get that savings as well. If you need to code additional non-repeated extensions and those require frame separators, you don't get the savings for the frame separators. And finally, it costs 1 byte to signal the repeat these extensions itself. So a couple of examples. All of these are with 3 by 20 millisecond frames in a packet. So if you have one L equals 1 short extension, so that's the L equals 1 means it has 1 byte of payload. You basically go from requiring a total of 9 bytes to encode those 3 extensions down to 6 bytes. So your 200% overhead gets reduced to 100%, which is still not amazing, but a lot better. So for another example, if you have 2 repeated extensions plus dread in the first frame, you save your 2 frame separators. You save the 4 extension IDs in the second and the third frame. And then because this now makes dread the last extension in the packet, you also save coding the length of the dread. And then the cost of that is you have to encode this extra RTE byte. So in total, you save 6 bytes per packet, which with 60 millisecond packets is only about 800 bits per second, which is, it's not nothing, right? So next slide. And the cost of that is, some amount of code complexity. So the main complexity is this section, which is taken from the extension iterator in libopus. So basically, the iterator is just iterating over each of the extensions in turn, and this figures out when you're doing repeat how to decode the next extension from the repeats. It's about 60. A little bit over 60 lines of code with comments. There's a few more lines elsewhere to set up the variables for this section, and the skip extension function in the original libopus has to get split into a skip extension and a separate skip extension payload. The second one is used if you already know the extension ID and the L flag, because those are implied. when you're repeating. So the overall complexity is a little bit more than this, but if you sort of squint, it kind of fits on one slide.
For all those 3-column code editors.
Right. Yeah, in any case, I think we've certainly done worse things in libopus. So those are the main trade-offs. If you want to go to the next slide. That was basically all I had to present. Would be nice to see more reviews and feedback on this, as I haven't gotten much.
Is that your last slide, Tim, or do you have one more?
The last slide is just a backup slide.
Okay. So at the last meeting, we asked for text and code complexity analysis. Tim has done that. As editor, I assume you feel safe and comfortable merging this, and you're just waiting for people to give you a critical review or a thumbs up, right?
Yep, I think that's accurate.
Jonathan?
Jonathan Lennox. I haven't read the details of the spec, but from what you presented here, I mean, it's sort of intricate, but that's what you expect from a codec to save bits, and that's fine. And until I had heard about John Mark's proposal for the enhancement layer, I wasn't sure that whether it was actually interestingly worth it, but now that that proposal exists, I think it is. So I'm in favor of this.
Thank you. Any other feedback, and specifically any objections?
Jean-Marc Valin. So as the maintainer who's going to deal with that, I'm actually fine with the code, and I think it normally should be merged. I think the only reason I would see not to do this is if anyone is working on, like, I don't know, mailboxes that are going to have to parse extensions and they think it's going to make their life really complicated. But otherwise, if that's not the case or anyone shows up, I think this normally should be merged.
I think that the goal is for middle boxes not to be parsing these extensions. These should be transparent in the opus padding. So hopefully should not be complicating the life of signaling entities. As the author, as editor of Dread, do you expect to use this? This has material benefit to you.
So in terms of Dread, that would actually not be useful for Dread alone, because Dread, you would only ever use one Dread, even if you have many frames. However, for other extensions, this could have potential savings.
Okay.
Only for extensions that you would have one per frame and not one per packet.
So even with 3 opus frames, there'll be one Dread extension for all 3 frames.
Yes, because Dread will ideally only be assigned to the first packet, because there's not going to be lost packets between the first frame you transmit and the second frame you transmit in the same packet. Okay. But for other extensions, it's got a purpose.
Jonathan Lennox again. I think I strongly suspect that if a middle box does need to parse this, and I think, like for some of the stuff Jean-Marc is proposing, it might actually be interesting to, do some manipulation of the packets if you're not doing end-to-end encryption, like, potentially stripping in the enhancement layers, sort of the equivalent of an SAC to go with SVC. But I think they probably just copy the code out of libopus, and that's probably going to be fine.
Okay. Well, hearing no objections, I think, Tim, you have the pin. Feel free to go ahead and make the change.
All right, thank you.
Any other issues left in that extension draft?
I think we still have to resolve the issue of whether or not we change the numbering scheme to support more varieties of short extensions, but
All right. Thank you, Tim. Next up, we have deep redundancy.
Have my slides.
Okay. You can try this, but I didn't have good luck. I don't even know what we're supposed to be pointing to. No, just tell me and I'll advance. Oh, I thought it was connected to this guy.
Okay. So this is an update for the deep redundancy in Opus. Next slide. So this is the update since the since last IETF. No real change in the actual spec, just more explanations that were added. So the new version adds the decoder architecture. This is an example of how it is described in a sort of functional notation. It vaguely looks like PyTorch TensorFlow. It is not valid PyTorch TensorFlow. And essentially the name of the layers in there match the string names in the weights file, in the binary weights file. So there's still needs to be a bit more explanation, but given that and the weights file, there should be a way to actually compute the entire output of the decoder. Next slide. So in the last meeting, we discussed a lot about how to publish the weights. So this here is a proposal that I'm seeking feedback on, because full reproducibility is really hard. So trying to get to something realistic that should hopefully be good enough. The idea would be to publish the entire training procedures. So have the Python scripts, any shell scripts up in the RFC appendix. The training data, that's about 100 gigabytes. We would need to figure out a place to put that, but it would, it is entirely freely available data. It could even be like scripts that download that data from the place where they are currently on the hope that they will remain there. And that place being not ZIF, but the actual OpenSLR in this case. And to some extent, that would mostly be useful to verify that the model is correct. You could not obtain a model from this data. We would, of course, also publish the output PyTorch models. And the whole idea of this is you would at least be able to verify that given the data, given the model, then the published weights are at least a minimum in the loss function for that particular data. It's not an absolute guarantee, but you would see that the model doesn't suddenly start drifting somewhere else, and you go like, this was trained on something else. So that's kind of what it would establish.
Jonathan Nixon, this time I did not put myself in the queue at all, so on average, I'm doing well. I think, speaking as somebody with some vague archival experience, I don't think we'd want to depend on third-party sites staying around. If the point is for this to be archival, we need to figure out how the IETF and or RFC editor are keeping their own archives. And I mean, you could certainly mention the provenance of each of them, but I don't think relying on other sites to continue existing, unless they're something that's committed archival work, and even then I wouldn't count on it. I'd say we should rely on our own archival policies, and probably we need to talk to the RFC editor about that, or whoever would be hosting it. The other thing,
so quickly, so I think there's also two levels of usefulness, like definitely the weights themselves, like those we want on IETF site because they define the standard. This thing that I'm talking about for the proposal is more about verifying that what we did is good. I mean, it's probably still good that people are able to verify later. Maybe there's better techniques,
Mhm.
but it is not necessary to implement the standard.
Right, but still, I feel like, I mean,
But
I guess it would be like, I don't know if there's such a thing as normative archive versus informative archive. Probably, I guess we're inventing both. But that's how I would sort of think about it.
Yeah.
The other thing I would suggest is the document should probably have like SHA-256 hashes of all the files in the document, so you can make sure you've got the real thing.
that is fair enough.
And whatever script that does the verification of the stable weights should probably also be in the scripts in the document. If you
Oh, yeah, that's what I put in. Like the scripts would be like
not
in
that just
the
the scripts you
appendix of
create,
the
but
RC.
the scripts that do the verification that you in your second bullet that verifies that the weights are stable.
Oh, okay, yep.
Good points. Please, note taker, add those points to the notes. At least the point about having some integrity check in the spec itself over the archival data.
Okay, next slide, please. Yeah, so, and you touched on this, basically current open questions are where do we publish the weights and where do we publish the training data and the training artifacts? I'm splitting those because obviously the weights are even more important, but there's about, 2 megabytes. This is the order of magnitude we're talking about. And the other stuff is more like 100 gigabytes. So, big difference in size.
Magnus Westlund. On the storage, I think you should talk to your AD. They might actually have, because I know there have been some other work who had the storage requirements into at least multi-megabytes range.
Okay.
So, yeah.
Okay, thanks.
And Magnus, where was the storage allocated?
I don't know. That's why you say ask your AD. Do you remember?
I think we asked before.
I think this is something that came out of some of Karsten's work somewhere, which so you get and prod your co-ADs to figure.
And that was it.
Okay. Thank you. Jan?
Yeah. Yeah, I will give an update on Opus speech coding enhancement. That's also over there. Next slide, please. So it's basically a two-part presentation. First, I want to give an update on the actual algorithm development. And then in the second part, I want to talk about the actual draft, which is about standardizing requirements to use these methods. Next slide, please. So previously, I presented two enhancement methods for wideband speech. Now I have a proposal for a blind bandwidth extension for wideband speech. And I mean, the motivation is we have two sources of wideband speech now. One is the Silk decoder itself. The other one is the vocoder that's used for deep redundancy decoding. And we can add a blind bandwidth extension algorithm to do wideband to full band extension. The result is a small DNN that has about 370K parameters and 410 megaflops. So the complexity is similar to NoLace, but the size is much smaller. It provides significant quality improvement. I will talk about this afterwards. It has the same delay as the Silk 16 to 48 kilohertz resampler, so it doesn't add delay if it's used. And there is code and model weights on the exp BWE branch of the Opus repo. Next slide, please. We conduct the listening test. That's a P808 DCR test. And what you see here is in black, that's Opus 1.5 at highest complexity, which means it's already using no-lace enhancement. And in blue, on top of that, that's Opus 1.5 plus this bandwidth expansion. And you can see that it improves quality at all tested points. Now the horizontal lines that you see, this is actually uncoded speech. So the lower line, that's wideband uncoded, uncompressed speech. In blue, you see uncompressed speech when adding the bandwidth expansion, and the top line in black, that's the full band reference. We did include a few interesting test points here that I wanted to highlight. So first of all, we compared against EVS, the super wideband 3GPP codec, and Opus 1.5 with enhancement and extension now matches the quality of that, which is a substantial improvement to what Opus used to deliver at this bitrate. We also compared to Opus 1.4. So you see this on the far right, Opus 1.4 at 18 kilobits per second, full band using the hybrid mode. And you can see that somewhere between 9 and 12 kilobits per second, maybe around 10, we need that quality. So it's almost a factor 2 bitrate reduction by adding these enhancement methods. And last but not least, for the first time, we compared against the fully neural codec, that's MLCODEC. And what you see is that at, I mean, one disclaimer, so it goes to way lower bit rates. It goes down to, I believe, 2 kilobits per second, maybe even a bit less. But what you see is that at 6 kilobits, it's still a bit better than Opus with all the enhancement, but at 12, it actually performs worse than Opus at 9. And it's likely a robustness issue. So compared to the samples that were posted with the original release, what we got out of this sounded substantially worse. And this is maybe just a thing to keep in mind, that it can happen with these data-driven methods. And so far, all the enhancements, lace, no lace, and bandwidth expansion, they turned out to be pretty robust. But for these purely data-driven methods, it can happen that you get, so to say, quality that's worse than you expect when you move to a new test set. And the test set here, it's recent high-quality data set years. It's called, yeah, so it's nothing unusual. Okay, thanks. And that's next. Oh,
Clarification question as an individual. So it looks like it's clearly, this method clearly has close to best in class in most cases, except for at the very lowest bandwidth.
yes.
Does EVS not appear because it doesn't have an operating point at 6K? And the same for encodec at 9K? Do they not have those codecs don't have operating points?
MLCODEC doesn't have 9, so it just has 6 and 12.
Okay.
EVS, I believe, probably has a lower operating point. The main reason I included 9.6 was actually that MLCODEC paper they tested against 9.6, and I wanted to have this kind of as a benchmark.
The encodec paper tested EVS at 9.6?
Yes, EVS at 9.6, and they had Opus, but of course without enhancements. Yes.
And even though they underperformed EVS, that's what they compared to?
So their results are considerably better. That's what I said.
Okay.
It's worse than expected, the results, and it's probably a domain shift issue.
Clarifications. These are subjective tests. They're pretty expensive. So
Yes.
you try to have the minimum number of points for
Okay.
what you're trying to show.
These are subjective tests that you produced, or is this someone else's subjective tests?
I produced them.
You ran the study. Okay.
Yes, but it's crowdsourced, so
Okay.
yeah. Yes. Any
Thank
other
you.
questions? Okay, then. Okay, the next slide, please. So at the moment it's still standalone, but this is how it would look, how it would be integrated into the Opus decoder. I outlined, so to say, the decoder as is. You have the CALT path, you have the silk path. You have mode handling that can be switching or combining a high band from Keld and a low band from Silk. And what you basically can do is, since it has the same delay as the current upsampler, so if you receive wideband speech or produce wideband speech with GRET and so on, you can actually, instead of just going to plain upsampling, you can go through the blind bandwidth expansion and you can get full band speech out. It's okay. That's it basically. So that would be the next step, to do the C implementation and integrate it. Are there any questions about this part? Otherwise, I would start with the actual draft updates. Okay, the next slide, please. So I worked a bit on the draft, and now I have kind of a full initial proposal about how to qualify a wideband Silk enhancement algorithm. So that would now refer to lace and no lace, not so much to the extension I just talked about. Next slide, please. So as a reminder, if you add enhancement to the Silk decoder, then you likely break the mandatory conformance test of the Opus specification. And the purpose of this draft is to update the Opus specification to allow for such enhancement algorithms, provided they meet certain requirements that will be specified. And I believe this is preferable to specifying the algorithms themselves, which one could also do, since it leaves room for future improvement. And it's likely that people will have better ideas, better algorithms will come up, and yeah, you don't have to reopen standardization for them. The goals of these requirements are actually, so the first one is to ensure that the enhancement algorithm works, it does what it's supposed to do, and it meets basic quality requirements. The second one is to make sure that the Opus decoder integrity is maintained, which means that switching, be it bitrate or mode switching, still works. And the last point is ensuring interoperability, so that whatever people do with these enhanced encoder, decoder, enhanced decoder with a legacy encoder still works for legacy decoders. Next slide, please. So about quality, the gold standard for evaluating quality is still subjective testing. There are objective methods, and they are also useful and convenient, but they are not entirely reliable. And what the draft says at the moment is that any Silk enhancement algorithm should undergo subjective evaluation before integration into the Opus decoder. It is a should and not must in a certain way, because the best method and test material, that can depend very much on what you want to do. And the alternative would be to put forward a mandatory test, say this is a testing material, these are the operating points, but it kind of defeats the purpose if someone wants to improve other operating points and then has to test on something that they don't want to improve. So it's a should to make clear one really should do this. And the recommendation is to use either P800, which is a laboratory test, or P808, which is a crowdsourced test, for evaluating genuinely new algorithms. And by a new algorithm, I would mean something like lace or no lace was new compared to lace. And it's understood that these evaluations are incredibly expensive. So we wouldn't recommend that you, whenever you tweak something a little bit, that you have to run a full scale new test, but still to make it clear that in these cases one should at least do informal listening to validate that the quality improvement is there. So that's what the specification says about quality so far. Next slide, please. Decoder integrity, this is now wrapping up many of the things I presented before. So it's a large-scale objective test, and it's based on previous experiments with the modified Opus compare degradation metric that's derived from the current conformance tool. It's a distance metric that has some psychoacoustically motivated operations in there. Um, and the data, that's now 81 languages and dialects from the Mozilla Common Voice data set. It's crowdsourced, so the quality varies. There can also be reverberation, there can be background. So it's very, I think, very relevant test material. And last time there was also a question about music. So there are now also 30 music clips from the Free Music Archive. So in total, it's basically 82 groups of test items. And it's now really about making sure that the decoder still works properly. So it tests a large set of encoder operating points. It's basically a product set. There are multiple bit rates plus bitrate switching. There is constant bitrate versus variable bit rates, 10 millisecond frames, 20 millisecond frames, multiple encoder complexity settings, and switching between Silk and Celt. Yes.
Another question as individual. The enhancement method is still strictly limited to Silk, right? It's a Silk speech
Yes.
enhancement method, but you want to run integrity on music and Celt switching just as a safeguard against breaking them?
It's a safeguard. So if you put music into the Opus encoder at 9 kilobits per second, it will be coded with Silk. That's what happens. So it can happen, and just to make sure that it doesn't get worse. So at the moment, surprisingly, it gets better with the speech enhancement methods. But at least you should make sure that you're not worse off than you used to be before. And switching between Silk and Celt, the main reason here is that you don't do modifications to Silk that breaks the seamless switching mechanism. Because you could basically alter the Silk path that much that you now get transition artifacts and so on. And this is basically to just checking. That's why it's called decoder integrity. Yes, please.
Jonathan, are you also testing the hybrid modes to make sure it doesn't screw up
Um,
the enhancements on the Silk side don't screw up once you add the Celt hybrids?
so this test doesn't do this because it tests 16 kilohertz. So it's an interesting question. So whether one should do this, and maybe this is one can address later when talking about how to test the bandwidth extension mechanisms. At the moment, it's basically the enhancement method won't do anything to the high band, and it's basically assumed that things should work out properly if it passes this. But this is kind of a to be done thing. But thanks for pointing that out. Any other questions? Otherwise, I would go to the next slide. So in terms what this means, there is now a folder called qualification that contains all the relevant scripts. There's a Python script that will run the test. There are test vectors prepared as input. That's about 4 gigabytes of data. And I tested them. So for lace and no lace, all tests pass. I also had this experiment where I used barely trained lace and no lace models to simulate a bad model or bad model behavior, and all tests fail. And more importantly, the margin is quite large, which means that we could leave substantial headroom for future enhancement algorithms. One important thing maybe to point out is also that no lace actually does worse in this test than lace. So it's really not a quality predictor. It's just a safeguard. Yes, so that's this part. And the next slide, please.
Just
Yeah.
one more question on this slide. So these test vectors, in other specs, the test vectors are usually just informative to help guide an implementation of whether it's correct or not. But in this case, do you intend for these test vectors to be part of the normative requirements for verifying that this extension, that this speech enhancement follows the right rules?
Yes, I would see it as normative, the same way as the test vectors for Opus decoder conformance are normative. at the moment.
Yeah, Opus was an oddball because, you know, most specs don't have the implementation in the spec. Okay, I guess we're continuing that oddness here.
Mm.
Okay.
I mean, in a certain way, you have to nail down the test or a test that makes sense, and that's one proposal to nail it down.
Okay, but the bulk of the draft itself will end up being algorithmic requirements, not just these test vectors, right?
It will. I mean, it will. Mm,
What are these test vectors? Are what
these
what is
test- these
what
are
is the
encoded
form?
bit streams. So, and I mean, the specification would just specify how to run this test. For instance, it would tell. I mean, the specification would nail down what you have to do in order to pass these tests.
But what is inside of that zip? What file is there? What is
Okay, the structure is there for every test, which means encoder operating point. You have a folder. In that folder, you have for every of the 82 sample groups, you have bit streams. What you're supposed to do is you take your enhanced decoder, you decode all these bit streams. You use the modified Opus compare tool to compute, so to say, the distortion of your enhanced output compared to a reference. And then you compare this to the reference score with a reference decoder. So it's also in the database. And then you have a rule that you cannot increase the distortion by more than a threshold.
okay, so this zip has Python scripts that implement the modified Opus comparison tool.
No, they don't. So they basically just have the data in this zip. Um, and this Python script for running the test, that's at the moment outside of the specification. So the specification tells you what to do. Just for your convenience, this script does this for you, so you can run the script, but the specification itself tells you what to do in order to pass the test.
Okay,
And
in English, not in Python.
Hmm?
In English, not Python.
In English, yes.
Okay.
And if you go to the next slide, I have, so to say, two to-dos that are left. At the moment, this modified Opus compare is implemented in Python. Oh, sorry, that's not the to-do. Let's take there. So the modified Opus compare is at the moment implemented in Python, and it uses NumPy. That's all not standardized. So what I will do is I will eventually implement this in C. It will be a short C program, and that will be part of the specification.
Okay.
So modified Opus compare, that's standardized. The draft says what you have to do to pass the test, and you have the data. That's what it looks like.
That's clear.
Okay, then for interoperability, this is kind of an odd thing. So at the moment, the Opus encoder provides a lot of freedom, what you can do. And what happens now if you have the possibility of having enhancement in the decoder that can provide an incentive to abuse this freedom? And I put together one example. I'm not sure whether it's a good one. So once you encode a bit stream, that bit stream is basically random bits if you've done it right. And you could get the idea that you want to signal some magic bits to a magic enhancement algorithm that's in your decoder. And now you can try to tweak the encoder within the freedom that you have just to get certain bit pattern out of your encoded frame. That would surely not improve the output of a legacy decoder because you have complete disregard of what you want to do there. It's rather a little bit like Bitcoin mining where you just want to get a certain prefix right. And I think this should be discouraged. It's now a new incentive. And the goal is basically to restrict this without imposing any, I mean, basically without making anything illegal that was legal so far. And the proposed requirement for this is to say that if an Opus encoder produces a bit stream that can be decoded into a reproduction of the encoded signal with an enhanced Opus decoder, then that bit stream must also result in a reproduction of the encoded signal when decoded with a legacy Opus decoder. So as long as you don't have an enhanced decoder, you can do whatever you like. But as soon as you have an enhanced decoder and you optimize for that, you have to take into account what a legacy Opus decoder would do with that. And the exact definition of reproduction of the signal, that's still TBD. Mo proposed to just say recognizable, which is kind of vague, but I think it's clear what it means. So I like that. Yes.
Maybe even human recognizable,
Yes.
in case people are
Human,
trying to use
yes.
this for, coding
Yes. Yes.
signals rather than speech.
Yes. Okay, then so the next slide, there are still these two or three to-dos for me. I will implement, as I said, this modified Opus compare metric in C. It's also that the current test vectors, they occasionally trigger PLC. And at the moment, the test only works if the enhanced decoder uses the exact same PLC algorithm. That shouldn't be. So what I will also do when the modified Opus compare metric is implemented in C, I will add, so to say, PLC masks to the test vectors, and then that will just be masked out, and that will surely solve the problem. And then in the end, we have to decide on final thresholds, and there basically the question is how lenient do we want to be, how much headroom do we want to provide for future methods. Yes, so that's the state of the draft, and my main question is if the working group finds the draft in its current form ready for adoption.
Jonathan?
Yeah, Jonathan. So this draft is both the description of the speech enhancement and also the rules for what you're allowed to do to a decoder and still be informant.
No, it won't describe the enhancement algorithms themselves. It will just.
Oh, so this is just what you're allowed to do
So what
and still be conformant.
Yeah, so whatever is in there in terms of description of algorithms, it's just for illustration. Yes.
All right. Yeah, I think that seems. I mean, obviously we need to get the details right, but as a general working group item, it feels like something that's certainly in the scope of things we would want to do.
Thanks.
So I guess another individual question related to that. It seems like the main utility of this is the actual enhancement, not the requirements for how the enhancement should not perturb regular decoders. So do you plan to integrate this into anything that the working group could access, or will it be part of an Opus 1.6 or?
I would definitely hope so. So the goal is definitely to make everything freely available. That's I mean, that's definitely true for lays. It's definitely true for no lays, and it's definitely true for this blind bandwidth expansion. Yes, so all of that would be, I think, part of libopus. That's the plan.
Yes, Jean-Marc. So just to make it clear, like the reason this is framed really as requirements is not because we want to keep everything to ourselves and just tell you what it achieves. It is all going to be available in open source. Maybe we can find a way of making it informative, but the idea is really to not say like what we're doing now is the be all end all. It's a demonstration of what can be done, and this is ML stuff. Like 10 years from now, we're going to have much better algorithms, and we would want to use these algorithms as opposed to every time come back to IETF saying, yeah, I got a new idea for a model. So that is really the goal here.
I mean, if there's anything you can think of that would make people feel more comfortable that all this stuff will be really usable under the current Opus license, then I'm very happy to do this. So there is no intention whatsoever to hold anything back. And yeah,
I think it's less of a worry about something not being available. It's more of a question of working group taking on something, understanding what the benefit to the working group is. If people are interested in the actual speech enhancement part, There may be less energy to just specify the requirements for it rather than working on the actual speech enhancement. But for them to actually work on it, they would like to see, what's there, whether they can build on. So, part of the question about adopting work like this, I think, is not just the requirements of not breaking Opus, is also, is there interest in people working on the enhancement part? And I think having a basis for that work would also be useful for those people.
Yes, but I mean, the basis for enhancement is there, right? I mean,
Lace, no lace?
lace and no lace is already deployed as part of Opus 1.5.
Okay.
The bandwidth expansion, that's also available in the Opus repo. So the methods are there.
Okay. So Jan has been diligently working on this for several meetings. I think there's been a lot of data presented that it has good subjective benefits. So I think the question for the group is, do we think that this work is something that people are interested in, and does it align well with the charter deliverable for improving Silk? Now, keep in mind, this is not the specific enhancement is not what we're asking as to be a work group draft. While that may be available in open source, I think the current plan is that would not be signaled, would not be standardized. It's just a decoder only enhancement. And so there is no need for any signaling or any standardization. The only thing that we want to make sure to standardize is guidance on how to not break interoperability when you do these extensions.
And updating the specification that you do not have to meet the current decoder conformance requirements.
How to break the conformance tests appropriately.
How to break conformance in an appropriate way. That's a good way to put it.
Okay.
Yeah, Jonathan, 'cause I see this as permission to do the enhancements, and then let people do the enhancements within this envelope we specify, to the best of their ability.
Okay. There's not many people in the room, so I'm a little hesitant to do a show of hands. So maybe we should just take this question of adoption to the list and hopefully get a wider response there. First of all, is there any objection from anyone to doing this work? Or any objection that Jan's draft is a good starting point for that work? Okay, for the notes, no objections. We'll just ask on the list if there's interest in this, and if there's no objections, I think we'll give you the green light to make it a working group draft. Greg, can you hear Jean-Marc?
I cannot. It was working before.
Try to just pop it out, see if when you popped it out, that it. Is there a battery or something? It's got a yellow flasher. I don't know if that means no battery. So another mic. Maybe just grab that mic off the back. Oh, it's is it green now? Can you hear me now? Yeah, there we go.
Mic crashing. That's nice.
Okay.
So this is a proposal for a scalable quality extension for Opus on the Kelt side, as Jan proposed something on the Silk side. Next slide, please. So Opus currently has the following limitation when it comes to the high end of audio and music. So the max bit rate is around 255 kilobits per second per channel, which means about 510 for a stereo stream. It has a maximum audio bandwidth of 20 kilohertz. It has a maximum per band bit allocation of about the equivalent of 8 bits of depth for lower frequencies and about 3 bits once you get close to 20 kilohertz. And the bit stream is a regular non-scalable bit stream. That's the current state of Opus. Next slide, please. And therefore, the scalable quality proposal would include essentially lifting some of these limitations. It would support more than 8 bits of depth per in different bands. It would support more than 20 kilohertz of bandwidth and support bit rates up to about 500 kilobits per second per channel. And in terms of compatibility, the whole idea is to do this in a way that is fully compatible with RFC 6716, so that a regular encoder and a new decoder will interoperate, and the reverse is also true. Next slide, please. So what are the applications of this? First one is there is clear industry and market demand for such sort of premium codecs. There are already several out there, and we believe that doing this with Opus while preserving compatibility is quite useful. But there are also other applications that includes non-audio applications. So, you know, sensors with wireless, with like ultrasonic sensors and that sort of thing, making recording, streaming that in a way that you don't care to listen to it, but you want to transmit the signal. So that is one definite use case of this. And also, still for audio, this would provide a scalable bitstream mechanism, which means even at 48 kilohertz frequencies up to 20K, just like we operate Opus right now, it would be possible to have a, let's say, a 256 kilobits per second Opus stream where you can simply remove half of the bits and get 128. So a bit like, you know, the audio equivalent of SVC, essentially. So that's another benefit of this proposal. Next slide, please. So the way that
grab the other one. I think it's maybe going.
Thank you.
Yeah, now it's red. It was yellow before. Now it's red.
For Friday, right? So this is how we propose to do this work. So use the extension mechanism that we're defining to add a new layer to Opus. This extension layer would have extra information. So first, it would include an extended resolution for the existing Opus quantizers. Some of the quantizers only go up to 8 bits, as I mentioned before, and we would just add the extra bits in the extension layer, and the decoder would use the original bits plus these refined bits to get the higher quality. A regular decoder will just not see the refinements, do everything fine. So that's one part of what would be in this extension, but also it would include extra bands beyond 20 kilohertz. So we would be doing this at a sampling rate of 96 kilohertz. That has to be a multiple of 48 for compatibility reasons, because some of the things are done in the time domain. And basically that includes the COM filter and the pre-emphasis that are time domain, so these require also slight updates, but that can work for they'd be fully compatible between the two versions. Next slide, please. Can I maybe? Oh. Sorry.
No extra chair, no meet echo, no AV support. Here we go.
So where does that fit? That is that it fits with current milestone number 4, that calls for extensions that improve the quality of Celt-coded audio. So we already have something in our charter for this. Next slide, please. And the current status of this, so there's no draft as of now. I got permission to open source very, very recently, but there is actual running code. It is not final running code, still a prototype, but there's this EXP QEXT16 branch on the GitLab repo, mirrored on GitHub. Yeah, so we're seeking feedback as to whether this is something that we should be taking on here.
Okay, Tim, go ahead.
You mentioned being able to use this as a layering mechanism. Does it just support one layer, or would multiple layers be possible?
Right now, it would be only a single added layer. More layers might be possible, but kind of a headache. So unless there's like a very clear ask for more layers, I think it would be just one added layer.
Okay. The other question is at 500 kilobits per channel, you're sort of entering into the realm of lossless rates. Will this scale all the way to lossless, or is that out of scope?
It is out of scope. The reason it scales all the way to 48 lossless, nowhere near 96 lossless.
Yeah. Okay.
And also it scales beyond 16-bit. So, 24-bit lossless is very, very expensive because the last bits are noise. So
yeah, fair enough.
We're pretty far from lossless bit rates here.
All right, that was it.
Okay, so to understand the ask, you want to know if the work group wants to take on some work like this. You intend to produce a draft anyway?
I intend to produce a draft.
Okay.
I'm just pre-seeking, seeing what the interest is to do this work.
Okay. I mean, just from a charter perspective, that's clearly within scope. So, you would clearly be able to present that draft here and engage people's interest in the room after they see the draft. Just as a quick understanding of the design, you expect to use the extension mechanism that we've defined. You expected this obviously not to be a blind extension. This will be a signaled, coded enhancement layer.
Yes, this will be
Normative
signaled,
encoder and encoder.
normative decoder, encoder can still do whatever it pleases using the extension mechanism that Tim presented. Obviously, lots of bits in the extension, but yes, it's fully coded, nothing blind in there.
Got it.
No, right now there is actually no ML in there.
Good. Yeah, we would look forward to seeing that draft, and I think people's interest will be gauged when they see the draft.
Great. So I'll be working on that shortly.
All right, stay where you are. One more.
Yep. So this is a second proposal for options for simplifications for the Opus codec. Next slide, please. So Opus has many tools, many different features in the specification right now, everything we could think of when we did the standardization more than 10 years ago now. Some of these features have proven very, very useful. Some of them are not used very much, but they're still in the spec. They're mandatory to implement. On the decoder side, the encoder is free to do whatever it pleases, but on the decoder, essentially what we're proposing is to make it sort of legal to skip a few of the features on the decode side that do not really affect interoperability. So for simplification purposes, clearly define what is okay to not implement in the decoder compared to the current spec. Next slide, please. So to give some examples of what we're thinking about, this is a strawman list of optional features we can think of. Maybe some people will say, hey, you know, I really depend on this thing, that don't put it there. And, you know, it doesn't have to be there. Maybe there's even more things that we're going to think of right now. But it's kind of a starting list to give an idea. One is right now we have normative mode transitions that pack a tiny 5 millisecond Kelt frame to sort of bridge between Silk frames and Kelt frames, and the reverse bridge between Kelt and Silk frames. And even right now, these transitions will be achieved using PLC if the encoder does not signal such a frame. So the feature basically just 100% ensures that there's not going to be any glitching when you switch modes, but most people never switch mode or do it like once every 30 minutes. So we don't think it's a huge impact if a decoder were to skip that feature. It turns out, to the best of my knowledge, FFmpeg decoder does not actually implement this. So we're just saying, let's make this optional. We would still keep it in libopus and so on, but if someone wants to skip it, that's fine. Another feature that is rarely used is the Silk stereo support. Typically, Silk is used in mono, and very often when you switch to stereo, Kelt mode kicks in anyway. So if we said that the stereo support is no longer mandatory, if you ever get a stereo stream, it would just be like discarding the side, but the mid would still be decoded, so everything would, you know, no speech would be lost. It's just the stereo aspect that would be lost if you didn't implement it. The third one is Kelt defined this folding mechanisms. When it runs out of bits, it says make something up. Right now it copies part of the lower spectrum using this folding scheme, but really any other injection technique that preserves the energy would work. And in fact, pretty much anything other that you could do would probably sound better. So this one, making it optional, could actually lead to increase in quality, or at least like it wouldn't have a huge effect. So that's, as I said, just a straw man here.
It may be dead, Jonathan. Yeah, so I just grabbed the speaker one again. You could try pushing the button on the bottom of it, but
yeah, no, I think the battery's dead. Would these changes pass the tests that Jen was defining earlier? Because if they would, then we don't need to say anything more than Jen's draft, right?
So I believe they would probably, first they would probably not pass, and second, yeah. And Jan's test is specifically for Silk, and some of these, like this Kelt folding stuff, would be for Kelt, and it's for music, so it's really two very different things here. Next slide, please. So essentially, these are sort of the benefits for this proposal. One, just generally more implementation freedom. There are smaller, it also would mean like smaller and simpler code for many of the embedded systems out there where, you know, code size is really an issue. And in general, like people are already sometimes cutting corners. So this would be like clearly specifying what is the right way to cut corners, and implicitly like what really you shouldn't be doing in terms of cutting corners in the decoder. That's it. And again, like we'd like to see what kind of interest there is in this kind of work.
Yeah, I mean, I guess sort of expanding on my previous thing, I feel like given how opus conformance is defined now, it'd be better to sort of define these as relaxed conformance tests rather than relaxed features per se. That's possible.
Yeah, again, I think this would be relatively difficult to do for reasons that each depend on what feature we're trying to remove. For example, stereo, suddenly, you know, you have this, you know, this signal that would be very different because, you know, the left and the right suddenly are identical instead of having like a large difference, and we would allow it only for silk and not for kilt. So having this sort of test, and it's similar for the folding stuff, like it may be possible, but I think I would be, for that one, I would feel a lot safer saying, what is the thing you're allowed to modify and in what way, as opposed to something that is attempting to cover all of opus, and then maybe we miss something, and then, yeah.
And another question is individual. Do you plan on making these things normative change in the bit stream itself? So the opus bit stream would be fundamentally different than what a standard opus decoder would normally get, or would some of them be, maybe can you go back to the previous slide on the actual mechanisms? Oh, I got it. Yeah. So
I think I understand your question.
yeah,
And
it changes the wire coding.
it does not change the on the wire coding. Like we preserve full interop, everything remains compatible. Right now, the encoder is free. For example, for the first one, the encoder is free to, when it changes mode, it can code this frame or it can not code the frame. If it does not code the frame, then the behavior is non-normative because it triggers the PLC. If it does code the 5 millisecond frame, then the behavior is normative and it has to be exactly that's decoded. So our test vectors include the such transitions. They do not include transitions without the redundancy because that's non-normative. So what we would be changing is the decoder would be free to say, even if a 5 millisecond frame was coded there, it would be free to ignore it and call the PLC and just not implement this part. But everything would still work. The encoder is already free to include this thing or not. Similarly, for Silk Stereo, what we're saying is the encoder right now is free to use Silk Stereo or not. What we're changing is to say that the decoder, even if Silk Stereo is used, the decoder is free to ignore it and decode normally. But every single one of these proposals result in full interoperability between an encoder, you know, encoders and decoders with and without the simplifications. That's the whole point of this. No interop is lost.
Okay, so there's no on the wire change if the encoder is blind to this. The encoder may still do something you don't want him to do. There is only a decoder change that potentially breaks some conformance tests, and you would relax those conformance tests to not care about that feature.
Yes.
Would you signal this at all, or it's just
No.
decoder only?
It's decoder only. Decoder is free to do whatever. Like, there's already a small amount of freedom on the decoder. For example, the packet loss concealment is not specified. We say do whatever you like for packet loss concealment. We would just be relaxing a few more things.
But realize that by simplifying your decoder, you're still taxing the encoder, not knowing that you're simplified, right? So the encoder still operates at full complexity, and that's not a concern.
So I don't have a strong opinion there. Like, we could definitely consider something where we define some SDP parameters where the receiver says, by the way, I have, you know, I'm doing these simplifications. Don't bother with stereo, or don't bother with these 5 millisecond Kelt frames. I think that's
Because what it sounds
it
like
would be a reasonable thing to do. Yes.
what it sounds like you're proposing in other standards is like, you know, constrained profiles. Other standards have concepts of profiles, and then simplified profiles are constrained profiles. It sounds like you're trying to introduce a constrained Opus profile here
So
that constrained decoders would.
only partially, in the sense that in many standards, when you have these profiles, if you mess it up or if you don't signal it, things break.
Yes.
Like if you say, you know, if the decoder says I only support the baseline profile and the sender goes full blast on the high profile, things break. In this case, it is just like every other Opus feature. It would be like, oh, by the way, if you send that, I'm not actually going to be using it. But if the encoder sends all of that, absolutely nothing breaks.
Okay.
So the signaling is just like we have signaling right now to say, you know, by the way, I support stereo, or by the way, I support only mono, so don't bother with stereo. But if you send me stereo, things are still fine.
Okay. So are you asking anything of the working group on this?
In general, like I'm mostly asking the working group, like if I were to submit a draft in this along these lines, you know, is that something that people would tend to support or be like strongly against, and you know, don't even bother submitting a draft on this? That's all I'm kind of seeking from the working group.
And to clarify, it's both proposals for new things to simplify and documenting what is already constrained in some implementations, like FFmpeg. You said FFmpeg doesn't already do the first one.
Yeah, I don't think documenting what everyone else out there is doing is really on scope unless there's a big ask there, but making sure that at least we have some guidelines about what is fine to skip and what really you shouldn't skip.
Okay. Okay, again, too few people to take a show of hands on anything, and I think people would be more interested in seeing a draft before making conclusions. So if you have the energy and time to work on that draft, individual draft, feel free to go ahead and bring it back to us, and we can make a more informed decision on it.
Or maybe like, is there anyone that really objects to this or thinks like there's strong concerns, or that's mostly what I'm trying to seek here.
Jonathan, I mean, I do think it would need to be well defined how it interacts with the conformance tests, which is to say, I have a decoder, you know, I want to see if this is a conformant Opus decoder, but I implement these things. What do I do in the test to say, yes, I pass?
Yes, agreed. That is not trivial to do, which means it's probably important to do it. So.
Okay, thank you very much. We look forward to a draft on this. Okay, that brings us to the end of our session. Any other business? All right, well, thank you very much. Enjoy the rest of your time in Dublin or at home. Have a good Friday night.
Thanks, everyone. Thanks, Mo.